Hi, everybody. Ouais. Okay, so Aline, are you? Well, we have 3 minutes left, and then we will start. Ah merde. Okay, so maybe I will start with a short introduction to Xiong and his talk. So Xiong Ren is a composer and researcher in computer music. He entered the Conservatoire National Supérieur de Musique et de Danse of Lyon in 2011, and he graduated in 2016. He also did a artist diploma and followed the cursus de composition at IRCAM. He is also a PhD student at Université Jean Monnet, and it's a very close collaborator with us. He did as I mentioned this morning, it is the author of the Faust IDE, and he's going to present us its last tool, and which it's the first public appearance, right, of Xiong of this tool.
Yeah.
Okay. So
first.
Okay. So Xiong, I think it.
Yeah. Okay.
Thank you.
Hi everyone. Yeah, I hope everyone had a good meal. And yeah, this is stream from China, so I'm hoping it's going smoothly. I'm going to share my screen, tab. Can you see my tab or this slide?
It's coming.
Okay. Yeah. So welcome to my presentation workshop. So this is a design pattern for Force DSP with a web-based graph editor. I would like to show you a tool that I made recently, which can be used for to design Force DSPs in maybe a more straightforward way, just in a web browser. So first of all, I want to talk about why I chose Force as the language to use in our DSP design workflow. Well, the reason is that if your DSP is already written in Force, it actually means that the DSP can be quickly exported with Force IDE or some online service or with your Force compiler to a large variety of platforms. And the other reason is that, which is also a most important one, that everything in Force can be considered as an audio stream. The Force, the name is combined from functional audio stream. So everything is audio stream and everything is functional. So the way we design Force DSP is just like connecting audio cables between different inputs and outputs from analog audio devices. So this reason actually brings us to the main purpose of this language. In fact, Force language is designed to be an interpreter to calculate from an audio graph to some machine-readable codes, low-level codes. So it provides a very efficient solution to let us be able to describe some complex audio graphs into plain text. Then it's up to the compiler to make these texts understandable by machines. This process is called block diagram algebra. So this block diagram algebra is the powerful side of this language that takes care of both human users and machines. Its text-based form might be a sweet point, but it is still not easy to learn. Maybe Jan, you'll not agree with that, but from my experience, it's not so easy because to write in Force, you need to learn how to manually translate a graph into the code. It means to flatten these cables and connections into plain text. And this needs sometimes hard work, especially for beginners, for some sound engineer, sound designer, or artists. So, for example, without compilation, there's also some difficulty that we don't always know how much inputs and outputs these modules actually have if you are importing these functions from the library. So fortunately, a bunch of tools are provided to make the coding experience much better. That is why I wrote last year with Graham's colleagues the new Force IDE, in which users can watch your block diagram of the code written in real time, and you can test it with multiple visualizations. You can debug it very quickly. And just in the browser. So this is a big step, or even like a game changer for us to make the language more accessible and user-friendly to Force developers. So after having this Force IDE, I'm thinking about if we can go deeper or go further to this user-friendliest way. So I can share this. Maybe later. I will post it in the chat. This slide. So here's as Force code is already a representation of an audio graph. why not just generate it from a graph automatically? And that's so that we can design a false DSP without any coding. Here's what I imagined. We can, from left to right, we can start from a graph in the browser. We can do some patcher, and it generates automatically the corresponding code for you. And then you can test it or having this block diagram to recheck if it corresponded to your graph, and just in time and just in the browser. So this approach is also used by Gen. If you're familiar with Max, you might know that Gen is also a graph-to-code generator. There's a language called Gen Expert, which is also an intermediate step between. Yeah, maybe. Yeah, it's the code is intermediate step between the graph and the DSP code. So you can also export this code into C++ code after you're having this graph or this Gen Expert code. So actually, I used Gen when I was making project in Max. So I think it would be nice if our forced graph-to-code generator can handle shares the same behavior as Gen to facilitate Gen users or Max users to switch to Faust and export maybe to more destinations or platforms. Here are 4 behaviors in Gen that I implemented in the Faust graph-to-code generator. First is these boxes that represent a function that takes some arguments or inlets. Note that if you predefine one of the arguments, it will actually replace one of these inlets and replace them into a constant value. Then graph connected with these boxes is called a patcher. Secondly, when Gen analyzes this graph, it will iterate all the outputs and search the connections above. So without any connection, its inlets will be the default value, so 0. Then multiple connections into the same inlet will automatically be merged and added together. So this is the second image shows, and beside its code. So the out3 is without any connections from its inlet, so it will be 0. And out1 is the merge of in1 and in2. And if you need to introduce a loop into the graph, it should be delayed by at least one sample by the history operator. So this is similar to Gen's tilde, which is recursive composition operator. And Gen also supports 2 types of subprocess. You can use a code box to write Gen's code, or put a subpatcher. These subprocesses are especially useful when you want to reuse it in different situations. And then with these basics, how do we generate the false code from a graph? Let's take a look to some examples from these functions. We know that all of them can be formed as one identifier as a result equals the function's name with parentheses and arguments separated by commas. So here, from right, we have ma.sr, which is the sample rate. It has no input, so no arguments. Then the sign has one input and one output. So here it's sign 0 because it doesn't have any cables connections. For plus, it has 2 inputs and 1 output, and the os.oscrq which is oscillator based on 2D vector rotation, is special because it has one input and two outputs. So we need to give an identifier for each of these outputs. So the code is a little bit longer. Here are some more examples to show how arguments and connections affects the code. With the graphs inputs, they have their index and identifier and can be composed easily as a function argument. In addition to Jan's argument usage, you can use an underscore as a placeholder that allows you to omit an argument declaration and leave it as an input. For example, here we have, from the right bottom, you have the en.ar, which is attack release envelope. It needs three inputs: the attack time, the release time, and the trigger signal. Here we fixed the release time, which is the second input, to 0.1, and the first input goes to attack time because we put an underscore at first position, and the second input goes to the trigger signal. You can also put a function name instead of the underscore or numbers to use it as an argument. Also, we know that for some pattern matching related post functions, the number of I/O is variable. It's more like the compiler doesn't know by default how much input and output these functions have if you don't put arguments before. So like here you have si.bus 5, sorry, it should have 6 input and 5 outputs. So where the number 5 already occupied the first input, so it leaves 5 available inputs and outputs. You can declare by @in6 and @aus5, like in Max. You can have these properties to force these input and outputs. And generating a graph with a loop is one of the trickiest things in this system. We know that in Faust we need this recursive composition operator tilde should be used in a loop so that we can identify easily every loop in the graph. And this is actually Yann Oglaré's consideration, and he proposed to put all these loops outside the rest of graph, and then to facilitate the cable management. So in this case, we have the main graph has 2 inputs and 2 outputs, where one pair of them are used to build the loop. Yeah, you can see in this block diagram that the loop is outside the main graph. And here's an example of code block subprocess, where you can have some Faust DSP code as a subprocess. You can put directly the Faust code into this code editor, and you can. I use here the environment keyword you can see in the code to ensure that the subprocess is in a closure. Then just export the process function. And after each change of the code, I evaluate the code in this box to actually get information about the number of inputs and outputs, so that the outer graph can connect properly with it. And I also implemented the subpatcher that will be transformed into a width expression, in which you can use identifiers that are defined at the patcher at the parent level of the patcher. So here you can see in the doc represents the contain the inner side of the patcher object, and it's a max with 2 inputs and 1 outputs, and this can be reused multiple times if you want to duplicate it elsewhere. Yeah, and here's something that is quite special in Force language, the iterators. More precisely, you have 4 iterators in Force language, which is par, sec, sum, and prod. They accept actually a subprocess with a variable that changes for each iteration and starting from 0. So this means the box that represents the iterator should have corresponding number of outputs with an additional variable output that attached to the subprocess. So here we have a par3 means 3 parallel processes as the output. So we have first 3 outputs, and with an additional one at the right side, the 4th one that will attach to our subprocess. And in this outlet, the variable iterates starting from 0, and we are going to have oscillators with 3 different frequencies. And this result of the oscillator actually connects back to par3 object in order to close this subprocess, and then the par3 can know which subprocess to iterate. And in the code, you can see this subprocess is transformed to a lambda function. The last thing we need in this system is some UI components. Just as declarations in Force, we can put some sliders, groups, knobs, and so on with its properties, the name, the main max, the default value, and the corresponding UI can also be generated in this web page. Okay, so yeah, maybe here we can start our workshop with some actual example of JSPatcher. Yeah, this environment is called JSPatcher, and I will post in the Google Meet this link so that everyone can play out. Yeah, and I propose you to open 2 tabs, one with this JSPatcher and another with Force IDE, so that we can easily test our generated code. And yeah, you are invited using Chrome browser, because this web app is really optimized for Chrome. Safari will not work, and Firefox cannot do some copy-paste stuff of patchers. Yeah, and note that I just finished this version with a file manager this week, and yeah, I think there will still be some bugs not fixed yet. So you can ask me in the Google Meet chat if you're having problems or bugs. Normally, you just do Command S to save, or Control S in Windows system to save your patcher and refresh the web page, and everything can be working. Yeah, and another thing is that we have some limits about WebAssembly's memory. So maybe you also experience with Force IDE is after too many times, if you compile these forced DSPs, it will reach the limit of WebAssembly's memory. So when you identify that Force doesn't compile in IDE or in JSPatcher, you just need to refresh the page. Okay. Yeah, I'm already sharing this environment into screen. So the first thing we're going to do is create from our file menu a new force patcher. So after doing this, you will have a tab called untitled.dsppat. dsppat is the suffix of our force patcher. And if you press Command S, or you can do also save from file menu, you can save this patcher to the file system. We will call it 01 dsppat. Yeah. But now you can see in your file manager panel, you have this this dsppat already here, and this file manager will not disappear even if you refresh your web page or you restart your computer. It will always be there. It's just when you make some modifications of this patcher, it will display a yellow point to say that you are not saved yet this modification. So just press Command S or Control S in Windows to save it. Okay, so for the first object we'll create is a comment box that you can type actually things in it. This is a comment. You can press C on your keyboard just in Max, or you can also press N to create a normal box, then type comment in it, and it will transform the box into a comment. And yeah, on the left panel, the first icon means you are writing the file manager, and you can also press the second one, which is a list of all the objects available in force patcher. So you can also type things in it and drag and drop the comments into the patcher. So that if it doesn't work, maybe it means your patcher is locked. So you can click on this lock to lock or unlock the patcher. So if it's locked, you cannot actually modify the patcher. In some cases, like the code, you can only edit the code when the patcher is locked. So yeah, you have two states of the patcher locking Max. So we were creating our first patcher with some math operations. Yeah, let's just start from a constant value. So if you press N and type C, you will have an object called constant or just C, followed by a number. We'll put 0.442 as an example. So in this, this box will actually output always the constant number 0.42. And we will create another object called out. Out1 means the first output. Just connect them together. And you can see in the code from the right side, you can press, click on this code button to show the actual code of your patcher, and you will see it already have the out1 equals constant, this constant box, which is 0.42. And actually this code changes when you have any connections changes in your patcher. So yeah, I will just put some comments here. Constant value. I do this. And if we are doing some math, maybe we will add some value onto it. just type n and plus space, then 0.42. And we'll create another output here, out2. Our output 2 is not connected, so it's 0. And when I connect it, it becomes the sum of these two values. You can also having plus object without any arguments, just have two inputs so that you can connect 0.42 onto it, and actually you will have the same result as out2. Yeah, then we will maybe do all the other operations, not plus, but minus. You can do Command D or Control D in Windows machine for duplicate these boxes. Double click the boxes to change the code in it. So this is the fourth output. This is the third, fifth, divide, multiply. Okay, now we are having all 5 outputs in this process. So let's just have it test in force ID. So I'm going to switch to force tab here. And copy paste the code we are having, and we will do an offline plot to just having these numbers on the screen. So put your plot mode to offline and plot first samples. Yeah, so now you're having strips with these values. I think they are correct. Okay. Yeah, I don't know if everyone got this result, but yeah, I think we will just continue. So this is our first patcher. Let's just save it, close it maybe, and create a second force patcher. So here we will do our classical example of the djembe example, when I think everyone, if you firstly you've opened the force ID for the first time, you will see this example, and it actually outputs a physical model of a string that repeats and repeats. So we will just put the code here. You can have a code block with the code object like this, and I will post this code, this example code here. So you know these objects of coming from first standard library, and here in force patcher you already have all of them. So if you see not seeing the objects.
Ren, we still see your Faust IDE.
Oh, sorry. I need to switch. Yeah.
Thank you.
Yeah, thank you for the reminder. Yeah. So here, I will redo the process. Don't worry. I will put code in object. I'll put a comment here. This is code block, and I'm pasting our example code. So let's do this example with a patcher. So you know, everything in false standard library are also available in this patcher. So you can find all this ba.posen, which is the one post every 10,000 samples function. So let's just put ba.posen and 10,000. It has one output and it will be connected to pm.gmb. With all these arguments separated by space, connected, and pm.revert demo. Revert. And this output of Jambe should be connected to all of these two inputs of the demo. And dispatcher will have two outputs. Connect them together. Now we open code and it will generate a code a little more complex from the original one, but basically it's the same. So we put this in port ID and we are having a diagram. And yeah, and to switch tab, yeah, we are having this diagram and we can run the code and it's working. So yeah, we will be able to run this code also in this JS patcher environment, but let's just continue with some other patches and test them in JS patcher. So yeah, I will just save this patcher as the second one. And we can start from build a third one, another patcher. Yeah, so in this patcher, we will build a very simple algorithm or DSP, which is the mean value of one period of incoming samples. So we will build a subpatcher and test it with the main patcher. So we can put a subpatcher here. You can put P for short or patcher. Yeah, the same thing. And you can actually double click the patcher to show what's inside. And you can also do Control Enter to display the patcher at the red panel. You can also modify it here. So we'll do this like this. So what's the algorithm for that? Basically, you have an input calculate, and you have a second input which will say how long this period is, how much samples you want to calculate for this main value. And the first thing we will do is delay our incoming signal for this period. We use this add to delay a false signal to some samples, and then you can minus the actual value from a sample that's is n samples ago, like this. And then we do an integration. Just add all these samples together between this period. So we need to add them together with a loop that feedback like this. And here we have the sum of n recent values. And the last thing is to divide it by the number of samples we measure. Output. You can see the algorithm here. And in order to test this, we may want a sample integrator with one value incremented each step by one. So the same thing here. Plus, we can do copy paste actually. Okay. And we also need to decide the length of our measurement. So let's put 400. And out one. Okay. So this should be, if it works as expected, after 400 values, you will have the sum, the mean value of these, of the sum of the first 400 value. So let's put the code in false ID. I don't know if the add doesn't exist. Maybe you are not in a false patcher, you are in another patcher. So make sure you choose the false patcher in your file menu. Let's put here in false ID and plot offline. And you will see here the 400 value, you will have a result of like 200 or something. So it works. Okay. The next thing, if we already have the algorithm of this mean value, we can actually build an IMS measurement in our false patch. So let's just save this one. Oh, I think we should do it quickly. So maybe just copy paste this patch again. So in order to do a RMS, which is root mean square, in fact, you have 3 steps. The first step is do a square, each values. And you already have the mean, these values. So we will put another 400 here.
Sorry, we are seeing again just the Faust.
Yeah, sorry. Sorry again.
Thank you very much.
Yeah. So I'll put some comment here. This is square. And you have the mean, and then the root. Okay. And we will be able to display the value in bar graph in posts UI. So it's called IMS from 0 to 2. And you will need a attach for that you doesn't lose your signal and the signal doesn't be considered as 0 of 1. This will show a root main square of the input value, and let's just test it in our patcher. So